Recording started.
Okay, so you guys all see that stuff that's on the screen there? Looks like some gooey mess flowing down. Perfect. All right, so we're just talking about viscosity right now, okay? And viscosity, as you might know, relates to the thickness of a liquid. So if you're talking about something like maple syrup, that's a really viscous liquid, whereas water is not a viscous liquid. It's called just a runny liquid, right? It's not a viscous liquid. So another thing we need to remember is that liquids become more viscous when it's cold and less viscous, sometimes that's a hard word to say, less viscous when it's warm. All right? So with, with that in mind, first question here, guys, how would you describe the viscosity of the oil you use in the summer and the viscosity in the winter? Okay, Hannah, go ahead. I don't think you really need to make notes, no. What I would recommend is if you want to watch it over again, you could always make notes then. But because the stuff's on the screen for the most part, I don't think you really need to make notes. Okay? So question, guys, how would you describe the viscosity of the oil in the summer as compared to in the winter? Let's start with the summer. How would you describe the viscosity of oil in the summer? Would it be low or high? What do you think? Okay. It's actually going to be low viscosity, and the reason is that when you have heat, heat makes a liquid less viscous, right? Like you guys know, if you boil some maple syrup, it's going to become less liquid, right? It's going to become more runny, unless it boils off the water, of course. So anyways, okay, so in the winter time, how's the viscosity going to be? Is it going to be high or low? That's right, it's going to be high viscosity or very, very viscous. It's going to be more like maple syrup, right? Okay, so now, in the summertime, what kind of oil are you going to use? Are you going to use a really viscous oil or a low viscous oil? Low viscosity oil? Sorry, I wasn't sure if you guys just typed something there. Sometimes I can't tell if it was the last question or not. So you're saying, Reese, you're going to use a low viscosity oil. Okay, now remember the thing is, if we're talking about the summertime, the oil is already really not very viscous. The viscosity is already low, so you want to use a high viscosity oil because it's going to get heated up and become less viscous. All right? So you want to use a high viscosity oil in the summer, and in the wintertime it's the opposite. You want to use a low viscosity oil because the cold is going to make it more viscous or more thick. Does that make sense, guys? Okay, so for question 2, we've kind of covered that already. It kind of makes sense? So just figure out what the viscosity is in the summer and in the winter, and you're going to use the opposite viscosity because you want to kind of balance it out and make it normal. Okay? So the question number 2 says, if you raise the temperature of a liquid, does it increase the viscosity or decrease it? What do you think? We've already gone over this pretty much. What do you think? Is it going to raise it? So if you raise the temperature, you're going to increase the viscosity. Remember, increasing the viscosity means you're making it more thick. Will something normally become more thick, a liquid, if you increase the temperature? It's going to become more runny, isn't it, if you heat it up? Because it's less like a solid. When it's like a solid, it's more thick, it's more viscous, right? So when you heat it up, it's going to be less viscous. Does that make sense? All right. So we've covered these 2 questions. I think we're done with this page. I'm going to go on to screen 2. Here we go. Okay. Now you guys remember talking about this guy named Pascal? He was a famous scientist, famous mathematician, and he came up with a famous law, And his famous law is that if you have a container, the pressure in that container, in other words, the air pressure, the atmospheric pressure if you want, is going to be equal in all directions. And if you look at the diagram, you can see that, right? It's got arrows in all directions, so it's pressing on all sides of the container equally. And so that law is used in a hydraulic pump. Now, you guys might not have seen a hydraulic pump before, but they're pretty cool, and I'll show you one on the next page. Okay, so here we go. All right, so here's a hydraulic pump. Now, here's how Pascal's law comes into play with this hydraulic pump, and I'm just going to bring up my little pointer here, okay? So, think about the inside of this as being like the inside of the balloon. If it's like the inside of a balloon, what can we say about the pressure that's inside this hydraulic pump? What can we say about it? High. How's it going to compare at the one end? Okay, this is the area of the pump that you press on, and this is the area of the pump that lifts something up. Is the pressure going to be different in those two areas, or is it going to be the same throughout the pump? So you're saying, you're saying no, it's not going to be different? And the rest of you guys are saying it's going to be the same. It is, right? Because Pascal's law says anytime you have any liquid inside something, the pressure is going to be the same throughout. So the pressure is going to be the same throughout. But what's not the same throughout, guys, is going to be the force. So if F1 stands for the force you're going to press on at one end of the pump, the other end that's going to lift the car is going to be a different force. You're going to press with a small amount of force, and you're going to get a large amount of force out of it. Because, I mean, you couldn't lift a car, right? But you could if you've got a hydraulic pump, because you only need to lift with a small amount of force. And here's the reason why you only have to lift with a small amount of force. We said pressure was the same throughout, right? Do you guys remember what the formula is for pressure? Anybody remember that? It's something divided by something. You guys remember what divided by what is pressure? Okay, it's going to be force over area. Okay, it's the amount of force you have in a certain amount of area. That's what pressure is. And a way to remember pressure, guys, you might remember, I think this was in the lesson, if you compare the idea of a lady's high heel shoe stepping on your foot, that's a lot of pressure, right? Okay, good. That's the formula. So that's a lot of pressure, a high heel shoe on your foot, right? But if somebody else presses with a sandal on your foot, if you're just taking a small area of your foot, you compare the area that the lady stepped with a high heel shoe, that's going to be a lot more pressure, right? It's a lot more force in that same small amount of area, right? So that's what we're talking about with pressure. Okay, so pressure is force over area. So the reason why this pump works is because you have small force over small area, right? This is small area here, right? Small amount of force you're pressing with. Here you're lifting a large area and with a large amount of force. But small force over small area equals the same thing as large force over large area. Does that make sense? So that's why the pressure is the same. It's like 4 over 2 would be small numbers, right? But they still equal 2. Or, 24 over 12 would be like the math you're doing with the car. Does that kind of make sense? You guys can feel the pain of the high heel shoe, eh? I've never had that happen before. I don't want to have it happen. Okay, so guys, this is what's going on here with the hydraulic pump. The pressure is the same throughout the fluid. We usually have an oil in one of these things, right? And but what happens is we've got a small force over small area on the one side, large force over large area on the other side. Now, we won't go there, eh, Hannah? Now, I know the answer is no. Unless we're talking like the special season of the year right now, or we're talking about right now, or something like that. Okay, so guys, I got a couple questions here for you. Question number 1 is, who can tell me what Pascal's law states? Okay, so Let's pretend I got a bunch of money in my pocket. $25 question here. What does Pascal's law state? Pressure is equal on all sides of the container. Good answer. Right on. Okay. You going to say the same thing, Logan? Sorry, don't mean to cut you off. Anywhere around it. Okay, so it's the same on all sides. Okay, we got question 4. Question 5. What is the same throughout a hydraulic pump system? What's the same throughout the whole thing? Pressure, right? Okay, so pressure is the same throughout the whole system. And what is different in the two parts of the system? Okay, you said air in which it is used. Remember, we're using oil, right? Force is different, right? Because force is small on the one end and large on the other end. Same with area. Okay? So you guys think you're kind of understanding this hydraulic pump stuff? Right on. You guys are good. Let's go on to the next one. Okay. Well, Logan, if there's anything you're not understanding specifically, just let me know, okay? And we can go over it afterwards as well, but feel free to stop me if there is something you want to go over. So we're good? Okay. So we're going to talk about these WHMIS symbols. WHMIS stands for Workplace Hazardous Information Material Systems, I think. Something like that. All right? So that's what these symbols are here. And so you need to know these symbols. They're in your textbook, and if you're not sure where they are, just look in the back of the book under WHMIS, okay, W-H-M-I-S. And so we're just going to discuss a few of these right now. I just want you to be able to identify, kind of match the symbol with the description underneath. So which one of the symbols has 3 circles in it? What is the symbol that has 3 circles? What is it telling us? Okay, it's kind of related to toxic. What does it say specifically? The one with 3 circles. Okay, starts with a B. It's biohazardous, right? You guys see that? This one right over here. Yeah, I think that's the word that Logan was looking for. Maybe he didn't want to type it out. Okay, so how about the one that's got a hand on it? Which type of warning symbol is that? Okay, corrosive material. And guys, what does corrosive material mean? If something's corrosive, it can eat your flesh. Yeah, that's right. So you don't want to mess around with stuff like bleach or any of that kind of stuff, corrosive material. So a lot of these, if you look at them, they're pretty well give you a picture of what's going on. Like flammable, that's pretty obvious, eh? With the fire, when it's got the death symbol with the skull and crossbones, immediate and serious toxic effects, all that good stuff, eh? No, maybe not. Okay, so we're not going to go too much into depth in these, but just go through them again in your textbook, okay? So you know how to match the picture with the description that goes with it. All right? So we're going to talk a little bit right now about just slurries. And so Alberta is famous for its oil, right? That's why we have, a fair amount of money in this province. And when our oil is extracted or processed in the processing plant, it's in the form of a slurry. All right? And so what is a slurry? It's a mixture of water and some sort of insoluble matter. Insoluble just means that the matter won't dissolve, right? So there's something that won't dissolve inside the water. And what it is, it's oil and sand. That's what doesn't dissolve. So that's what makes the slurry. Okay? So yeah, that's what the oil sands is. It's a slurry. Okay, so here's something, guys. Solutes, solvents, and solutions. This is really important because some students kind of find these ones are a little bit easy to mix up because they all start with S maybe, I'm not sure. Okay, so let's just say what they are again. So solutes are the substances, they're usually solids, that dissolve in other substances, usually liquids, called solvents. Together the solute and solvent make a solution. Alright, so question for you guys. Can you take solute, solvent, and solution and make kind of an equation out of them? I realize we're talking about math here, or science I should say, but if you kind of made it into a math equation, how would you do that? You're going to take solute and solvent and solution. How would you do that? Just to give you a picture of what's going on. I'll give you a hint. You use a plus sign. You take those three words, solvent, solute, and solution, and give me an equation that shows how they're related. Solute plus solvent equals solution. Perfect. Okay, does that make sense, guys? And now all you need to remember is that the solute is the thing that's dissolving into the solvent, and together they make up the solution. Can you guys think of an example of a solution? Okay, gold. Gold dissolving in what? Okay, yeah, you got the right idea, Logan, too. Okay, so it's got to be some sort of solid dissolving in a liquid. Or it doesn't have to be, there's other kind of solutions, but that's the kind we normally think of, right? Okay, how about salt and water, right? You put a bunch of salt in water and you mix it up, and you don't even know that it's salt in there necessarily unless you taste it. Okay, so good stuff. All right, so solubility is just a word that describes how well a solvent can dissolve a certain solvent. Okay, so how well something dissolves is solubility. That's all that word means. And we're usually talking about a certain temperature because if you heat something up, it's going to be able to dissolve more solute than it could before, right? Take a chunk of sugar and put it in some tea. It's not going to dissolve that well until you heat it up. Then it'll dissolve really quickly, right? So the more we heat things up, the more they dissolve. All right. So, yeah. So question 9 says, explain the relationship between a solute and a solvent and a solution. I think we've done that already, haven't we, with our little equation. So I don't think we really need to do that. We know that a solute dissolves in a solvent to give us a solution. Good stuff. Okay, so here's a question. How would the solubility of water in an oil sand slurry compare to the solubility of other substances in it? Okay, so what would you say about water and the other stuff that's in the slurry? Which one has high solubility, which one has low solubility? Yeah, sugar and tea is good. Okay. Basically, what I'm trying to get at here, Hannah, is the stuff that's in an oil sand slurry. You've got some other stuff that's in the water. The stuff that's in the water, what is that stuff again that we find in the water in an oil sand slurry? You guys remember what it is? Sand and what else? Good. Sand and water. Okay, oil and sand in the water. The oil and the sand, do they dissolve well in the water or not? That's right, they don't. And that's why it's called a slurry. So that's all I was trying to get at in this question. I was just trying to get at that the solubility of the other substance is not very good. The sand and the oil is low solubility. The solubility of the water, you could say, is high. Okay? That's all I was asking for this one here. So we're going to go to the next one. Screen number 6. Okay, so now we didn't lose somebody, did we? Yeah, I'm not sure what that ding was. Anyways, okay, we're going to talk about compressibility. Okay, that's all right. So you guys know from personal experience that air is more compressible than water, right? And when we talk about compressible, we just mean easy to press together. So if we had a pump that was filled with air, just imagine you've got some pump you've got sitting in your garage, and if it was filled with air, it would be easier to press that handle down than if it was filled with water, right? But the question we want to know here is why? Why is it that liquids are more, they're not as compressible as air is? And the reason is that liquids have more particles in the same amount of volume compared to gas like air. Okay, so that's why air is more compressible. So since particles are harder to press together than empty space is, that's why liquids are less compressible. Because a gas is actually mostly empty space. That's most of what it is empty space. Okay? So we got some blanks here, and we got to try to figure out this information we've got in the paragraph, and we're going to put that information into these 3 blanks. Okay, so let's see if we can do it, guys. Something is less compressible than something. What do we put in the first blank? Okay, liquid is less compressible. That's right. Liquid is less compressible than what? Than air or gas. You guys are right. Because why? Why is liquid less compressible? What's the reason again in the third blank? Okay, more or less spread out. So the particles are more spread out when you're talking about air. And they're less spread out. They're close together, and they're bumping into each other with a liquid, and that's why you can't compress it so easily. All right, good stuff. There we go. I was trying to put a happy face here, but there we go. Ah, okay. All right. What else do we got here? We got stars. All right, enough fooling around. So, we're going to talk about density right now, okay? And don't say when you're talking about density, that's my brother or my sister, right? Don't want to say that. That wouldn't be good. But we're talking about dense substances, right? And a dense substance, if you compare like a box full of bricks or a box full of feathers, you got the boxes the same size, right? In other words, the volume is the same for the bricks and the feathers, but the bricks have more density because they've got more mass in that same amount of volume. Okay, so we look at the formula density equals mass over volume. You're comparing the 2 boxes. They both got the same volume, but density has more mass, and that's why density goes up when mass goes up. All right, so density equals mass over volume. Okay, no comments about your brother here. So, how does density change when we heat things up? When we heat a substance, the particles gain more energy, right? They get bopping around. They bump into each other. As they bump into each other, they spread out. So we got to think about what's happening when things spread out. What happens to them? Okay, well, you end up with less particles in the same amount of space because they're bumping into each other. So guys, what do you think happens to the volume when you heat something up? Does the volume increase when you heat something up or decrease? It increases, right? Stuff spreads out. If you've got a balloon and you heat it up, it's going to get bigger. The volume's going to increase. Okay? So what do you think is going to happen to the density if you heat something up? Do you think the density will go up or down? Well, think of it this way. Density is kind of like thickness. It's kind of like the thickness of a substance. So if you heat it up, do you think it's going to become more dense or less dense? It's going to become less dense, right? Okay? It's just like before we said it's going to be less viscous. That's another way of saying less dense, right? Does that make sense? Okay? So when the mass of something goes up, then its density goes up. But when the volume of something goes up, then its density goes down. Right? Okay? So heating up a substance reduces its density. And it also reduces its viscosity. All right. I meant to ask you guys a question earlier when we talked about viscosity. I'm just going to quickly go over to the first screen again, then I'll come back to this one, because I think we missed a question. And the question was number 3 here, which says, what type of liquid would a marble drop fastest in? Would a marble drop fastest in a low viscosity liquid or a high viscosity liquid? It's low, right? Because a low viscosity liquid is really thin, right? It's the opposite of maple syrup. And you put a marble in that, it's going to drop really fast. Does that make sense, guys? Okay, so you just got to think through what the words are meaning with high viscosity and low viscosity. How low can you go? Okay, so back to this here. I just remembered all of a sudden somehow that we forgot that question, so just wanted to cover that. Okay, so I got a picture here, guys. This is a picture of a black hole. And I don't even know how they can take a picture of a black hole, but the reason I wanted to show you guys that was just for fun. And a black hole is something that sucks stuff into it, right? You know, like if you got anywhere close to a black hole, it would just suck you right into it because, you know, the more something weighs, the more you're attracted to it, right? That's why you're attracted to the Earth, because the Earth weighs a lot. And if you were anywhere near a black hole, it would suck you in, and it sucks the light right into it, and that's why it's black, right? Light can't even get out of it. But I was just wanting to show you guys this because if you were able to take like a teaspoon of a black hole, if you could do that, that would weigh so much, that would be like, I don't know, as much as a small planet or something like that. So you guys, you know, I can see it looking like a chicken. I kind of see what you guys are saying. It kind of reminds me of looking at clouds too, but it does sort of look like a chicken. So I'm with you guys on that. But just so you know, it is a black hole, okay? So maybe we can say black holes look like chickens. That's your science for the day, hey? All right. So guys, we're going to talk now about the 2 main kinds of matter. All right? And the 2 main kinds of matter, let's get my little pointer out here again. 2 main kinds of matter, okay, now I got a star. I don't want a star, I want a pointer. 2 main kinds of matter are pure substances and mixtures. And why are those the 2 main kinds of matter? Well, pure substances are just one kind of substance, whereas mixtures are more than one kind of substance mixed together, right? That's why they're called mixtures, because they're mixed together, more than one substance. Okay, now pure substances can be different things. They can be elements, or they could be compounds. So you guys remember elements are like just one thing, like copper or oxygen or, you know, whatever is on the periodic table. Okay, hand raised. Okay, so Logan, you're saying you can't see anything on the screen? I think Logan was just wanting to let me know that he couldn't see anything. Are you saying you can't see what's on the screen right now about pure substances and mixtures? Huh. Can you guys see it okay? The rest of you guys? Okay. All right, I'm not sure what might be happening there, Logan. Did you press anything that could have done anything? Okay. Well, I'm not sure. Let's see if it gets back to normal on the next screen. So just hold off on it for now. And when we're done the recording, you can look back on this screen and then you can see it properly, okay? But just listen for now. And so we're talking about pure substances and mixtures, okay? And we said mixtures are just one substance, pure substances are just one substance. Mixtures are two different substances mixed together. And pure substances could be elements or compounds. So elements are things like copper, whereas compounds are things like NaCl. That's table salt, right? You got two elements together to make a compound, Na and Cl. And now mixtures, you could think of like sand. That would be an example of a mixture. Okay? So question for you guys, number 13. Why is HCl, which stands for hydrochloric acid, now that's the acid that's inside your stomach, that's eating away at things to break them down, right? Break down your supper. Why is hydrochloric acid a pure substance, and why is something like salsa a mixture? Can you guys explain that? Okay, remember, Logan, we got to think back to the definition of pure substances and mixtures. What's the difference between the two? Right? If you think back to that definition, okay, salsa has like peppers in it. HCl is natural. Okay, mixture is more than one thing. You're right, Ariel. So because it's more than one thing, salsa is more than one type of thing, right? It's got onions, it's got tomatoes. It's not just one compound, right? Whereas if you're talking about HCl, that's one compound. All right, so does that make sense to you guys now? It all comes down to the fact that a pure substance is just one type of thing, whereas a mixture is two things, two or more put together. And salsa is two or more things put together, whereas HCl is just one thing, even though it's got two different elements in it. Okay, so let's go to question 14. Okay, I'm not sure who's moving the thing around there, but if you could please not do that, okay? All right, so question 14 says, what are the two main kinds of matter? So do you guys remember what they are again? Two main kinds of matter. Pure substances, that's good. Okay, what's the other one? And mixtures. Okay, two main kinds of matter. Good stuff. All right, you guys got it. Let's go on to the next one. Yep, you guys all have it. Okay, right on. So we're going to talk now about concentrated and dilute. And we're going to see these two words mean different things. Okay, so what did concentrated mean? Well, sometimes maybe your mom or whoever's doing, the laundry around your house talks about, concentrated Tide. They talk about that on TV, right? Commercials for Tide, it's concentrated, it's better. It's more powerful. Well, why is it more powerful? Because it's got more solute dissolved in the same amount of solvent. Okay? Yeah, so you guys do the wash, eh? Okay, so that's concentrated, more solute in the same amount of solvent. All right, now, if you're talking about something dilute, it has only a small amount of solute in the same amount of solvent. Okay? So, when a solution's saturated, that means you've got as much solute as you can possibly dissolve. Okay, so you try to keep throwing more salt into the water, and it doesn't dissolve after a certain point. Why doesn't it dissolve? Because it's saturated. Okay? So no more can be dissolved. That's what we mean by a saturated solution. Okay, so we've talked about concentrated, we talked about dilute, and we talked about saturated. So, question 15 here. Write a formula for concentration using solute and solvent in your formula. Okay, so we're doing math here again. So write a formula, and it's got to have solute and solvent in it. So what would your formula be? You can look up above on what's written here. By the way, are you able to see it better now, Logan? No, eh? Okay, well, have a look later on at the recording. I'm not sure what's going on, but... Okay. So we said that it's a certain amount of solute dissolved in a certain amount of solvent. Here's what we do for the formula, guys. Concentration equals the amount of solute in a certain amount of solvent. So we say it's amount of solute divided by the amount of solvent. Okay, that's what concentration is. So we're talking about like 5 grams in 2 liters. That would be the formula for concentration. Okay? So, that's all right. So we got question 15. We got a formula for solute divided by solvent equals concentration. Now for question 16, it says a concentrated solution has a lot of blank in it. What goes in the blank there? Concentrated solution has a lot of what in it? A lot of solution in it? Okay, think hard, Logan. Remember, okay, it's a lot of solute. A concentrated solution has a lot of solute in it, right? Because concentration is the amount of solute dissolved in a certain amount of solution, or solvent, I should say. Okay? Okay, so a concentrated solution has a lot of solute in it. A dilute solution has a lot of what in it? What would we put in that blank? A dilute solution has a lot of what in it? You keep dying down, eh? Maybe I was leaning back. Does that sound better? Okay, I'll try to keep leaning forward. Let me know if it does that again, okay? Okay, so Hannah said it right. A dilute solution has a lot of solvent in it, which is the same thing as saying that a dilute solution has just a little bit of solute in it. So does that make sense, guys? The difference between concentrated and dilute? Concentrated, you got a whole bunch of stuff dissolved in there. Dilute, you have only a little bit of stuff dissolved in there, but you got a lot of solvent. All right. So, next question. A blank solution has as much blank in it as it possibly can. What do you think goes in the first blank? What word do we use to talk about a solution that has as much of something dissolved in it as it possibly can? Saturated. Okay, so a saturated solution has as much what in it as it possibly can? So saturated solution has as much solute dissolved in it as it possibly can. That's right. Okay. So I think, guys, if I'm not mistaken, I think we are, oh, we're very close. Just a little bit more to go. All right. So we're going to talk now about pumps. And so pumps are devices that move fluids from one place to another. Now, if you guys are like me, whenever you hear the word fluid, you automatically think liquid, right? Well, there's going to be similar questions on the test. I'll say it that way, okay? So that's why you really got to pay attention to this stuff. All right, but are you guys like me that when you hear the word fluid, you think fluids are liquids? That's what I've always thought, you know? But fluids are actually liquids and gases. Both of them are fluids, okay? Because both of them flow. That's what we mean by a fluid, okay? So there's 2 different types of pumps we can have depending on what kind of fluid is in it. If we have what's called a pneumatic device, then it's got air in it. So like your regular air pump that pumps up your air mattress, your ball, whatever, that's a pneumatic pump. But if you've got a hydraulic device, it's got liquid in it. And we saw that earlier, right? Okay, so that's the difference between a pneumatic pump and a hydraulic pump. Okay, so let's just go over that again. So guys, what's the difference between a pneumatic device and a hydraulic device? Or we could say pneumatic pump and hydraulic pump. What's the difference between them? What do you think, Logan? Okay, but they use two different things in them. Do you remember what the two different things are in a pneumatic pump and a hydraulic pump? I realize you can't see right now. You can't see the stuff on the screen, Logan, so it's a little more difficult. Yeah, you're right. Well, oil and air, or liquid and gas, right? So liquid is which one? Pneumatic or hydraulic? Okay guys, let's focus, okay? Liquid, pneumatic, or hydraulic? I know you guys know this. Okay, we need some better spelling here. Hydraulic. Yeah, that looks a little closer. Logan's looks a little closer. Hydraulic. I know they're long words, you're right. Okay, so hydraulic has a liquid and pneumatic has a gas. Okay, so here's a true and false question. Only liquids are fluids. Is that true? Only liquids are true? Or only liquids are fluids? It's false, like you guys are all saying. Okay, all right. We got the idea, Logan. All right, so next part, pascals and newtons. All right, so we're back to this Pascal guy. Okay, so remember a force is measured in newtons, right? And a force is any push or pull on a substance. So if you're pushing a fridge, that's a force, or if you're pulling a fridge, that's a force, right? And believe it or not, guys, if you push on a fridge and it doesn't move, in science, it means you're not doing any work. And I know that sounds weird, but in science, you're only considered to be doing work if something actually moves. I know it sounds weird, because if you're pushing, you're still sweating and stuff like that, but it's not work. Okay, so force is any push or pull on an object. And we know that it's measured in newtons, and pressure, we already know from before it's measured in pascals, right? And you can remember the P's. So pressure starts with a P, Pascal starts with a P, right? Okay, so true or false, pressure is measured in newtons. What do you think? Okay, remember the P's. Pressure, newtons. What do you think? True or false? Is pressure measured in newtons? It's false. What's it measured in? Reese, what's it measured in? Starts with a P, just like pressure, right? What's it measured in? Pressure. Pressure is measured in pascals, right? Force is measured in newtons. Okay? All right. So, we are on screen number 11, and we're getting pretty close. So, I just wrote down here, do you remember what makes a substance a pure substance? A pure substance is all one kind of matter. So pure substances can be either elements or compounds. We already went over that before, right? Substances that are a mixture of more than one substance, like sand. Now, vinegar is a solution. Even though it looks like it's made of just one substance, it's actually made of two. Okay? It's got acetic acid and water. So what do all pure substances have in common? How would we describe a pure substance? It's a definition for one. Remember this part right up here? It's a definition for a pure substance. Okay, it's always just one kind of matter. Now, it could be an element or it could be a compound, but it's just one kind of matter. Okay? And I wrote a little thing at the end. I wrote, "This is the end." I found a nice little picture on the internet. Sorry, Logan, what do you mean there when you said you don't know what I'm talking about here? Oh, you can't see my little picture on the screen? Is that what you mean? Yeah, someone said, did some graffiti here on the screen and it says, "This is the end." Okay, so that's the end of our session, guys. So Logan, please have a look afterwards. I'm really not sure what happened. Somehow your visual stuff didn't work, but have a look later on. check it out. I'd recommend all you guys have a look at the recording again later on to get to know everything really, really well. Okay? And thanks a lot for your participation in the session, guys. And also wanted to just say again, if you could please let me know, like send me an email after the session just to let me know when you're going to be writing your test, okay? Sounds good? You know, basically any time before Monday, because that's when I'm doing the report cards. So I would say, you know, first of all, have a look at this recording again, and then, you know, you can do it. I'd recommend, you know, looking at the recording again either today or tomorrow morning, say, and then doing the test tomorrow might be a good time, or you could do it on Friday as well. Alrighty? You could do it today if you wanted to, yeah? It's up to you.